not clear, please write on the chat box. Okay, that's fine, Hamza. That's fine. We will meet after 10 minutes. Hamza, now it's okay.
Yes, sir.
Okay. So actually the system is not working properly. So we have this question. Okay, Hamza. So let's see. Two charges minus q. This is minus q charge, and this is plus q charge are located at points, this point and this, respectively. Okay. How much work is done in moving a test charge from point this to this? Okay. So this is x-axis, y-axis, and z-axis. Minus q charge is located at 0, 0, minus a. At 0, 0, minus a means along the negative z-axis. Okay, this is negative z-axis. X coordinate is 0 here, y coordinate is also 0. This point has only z coordinate. So this point will lie on z axis, somewhere here. And this is minus q charge, and 0, 0, minus a. And another charge p is placed here, 0, 0, a. Okay, and this is origin. So Hamza, what is the distance between point O and point B? Hamza,
Yes, sir.
what is the distance between the point O and B? A, na? This distance is A. This is origin and this is point B.
Yes.
Distance is A. Okay. And what we are doing, we are moving a test charge, from point P to Q. Okay, so actually we have already solved this type of question. This is x-axis, this is y-axis, and this is negative x-axis. Okay, this is negative z-axis. So this point P will lie here on x-axis now, 7, 0, 0, and this Q point, where the Q point will lie, on the positive z x-axis or negative z x-axis. This is point Q, minus 3, 0, 0. Okay.
Yes.
So Hamza, this is a dipole. This is, here is minus Q charge, here is a plus Q charge. Means this is a dipole, na? AB is a dipole. And we have studied that if this is a dipole, this is charge minus Q and this is charge plus Q. And if I want to calculate the potential at the equatorial position, so I have told you that this will be 0. Told you now? Okay. So this z axis is perpendicular to this x axis. Okay. This is z axis. These all axes are mutually perpendicular to each other. Okay. Suppose this is x axis and this is y axis. So they are perpendicular, and this is z axis. This is also perpendicular. So this condition is like, you can imagine, this is the dipole, and this point Q for this dipole is the equatorial point. This point Q I am writing here for dipole. Hamza, are you getting my point or not?
Yes, sir.
Actually, Hamza, let's see. This is the dipole actually, minus Q and plus Q, and this is separated by some distance. This is a dipole, and there are 2 points given in the question, and these points are on x-axis. This point is on positive x-axis. This point is on negative x-axis. Okay, and actually this dipole is perpendicular to this point Q. This is like this. This is like this, na? Actually, you should imagine this in 3D. Are you getting my point?
Yes, sir.
Like this. Give me a minute. Now see here. See here. This is x-axis. This is y-axis. Okay. And this is z-axis. This is like this. Okay. These axes are like this. Are you getting or not? This is x-axis, this is y-axis, and this is z-axis. And these all axes are perpendicular to each other. Perpendicular to each other means x-axis is perpendicular to y-axis, and x-axis is perpendicular to also negative y-axis. They all axes are perpendicular to each other. Okay, so this is the thing. So it means that this is the dipole. Dipole is on z-axis. For dipole that is on z-axis, point Q is equatorial point, and due to the dipole, the potential due to the dipole, the potential at equatorial point is, what is the value? At equatorial point the potential is 0. Okay, this is point Q, and this point Q is equatorial to this dipole, means the potential at point Q due to this dipole is 0. Why this is 0? Because we have discussed that. Hamza.
Yes, sir.
Hope you have remembered.
Yes, sir.
Okay. So I am writing here VQ is equal to 0. No problem. Now I want to calculate the potential at point P, and this point P is also at the equatorial position. This point P is also at the equatorial position, means like this is the dipole. This is the dipole. Like you can say this is a dipole, and okay, let's see. This is a dipole and this is the point P. And I can, if I will do like this, then this will be the equatorial position of this. So means here also the potential is 0. Okay, Hamza? So this is not very complex question, it's an easy question, but you have the knowledge of coordinates. You can solve this question in 30 seconds also. Vp is equal to 0. And now what we are doing? We are taking a charge, we are carrying a charge, we are, okay. I don't know what is happening today. Bad one. What is happening here? Okay, no problem, we will fix it. Okay, my laptop I think not working properly, or maybe there are some other problems. We have this section, nothing in this section. We have this section. Now this section is completed. So the assignment, this is this section. Got the point. Okay. Please wait, Hamza.
Yes, sir.
Where that question, that thing has gone. Okay. Now what should I do? This is the, so again I am making the right. No problem. So Hamza, let's see. This is our y-axis. This is our x-axis. This is our z-axis. And this is negative z-axis, x-axis, and this is negative z-axis. And here minus q is placed here at point A. Minus q charge is placed, and the coordinates are 0, 0, minus A, and at point B a plus q charge is placed and coordinates are 0, 0, A. And here the point is P, and here 0, 0, 7, and here is another point Q, that will be minus 3, 0. Now what we are doing, we are moving a test charge from point this to this, means from point Q to, from point P to Q. Means what we are doing, we are taking a charge and we are taking a charge to the point Q. Suppose we have taken a test charge. You notice test charge. So they have asked how much work is done, and we know work is charge, the value of charge into change in potential, and W is equal to Q naught, and we have calculated the potential at point Q. Means delta V means final potential. Final potential means potential of Q minus potential of P. As these are equatorial positions, as I have already mentioned, so means here the potential is 0, here is also the potential is 0, means the work done is 0. This is the answer. Okay. And Hamza, remember, this is very good question. And this question. Another question of test. I have asked in this question, what are the points at which electric potential of dipole is maximum? Electric potential of dipole is maximum. What are the points? So suppose this is a electric dipole. And what is electric dipole? Two opposite and equal charges separated by some distance. And this is distance, we have considered this distance A and this distance A. And they are saying what are the points at which electric potential of a dipole has a maximum value. So we have a formula for dipole at general point, like this is theta and this is point P, and if I want to calculate the value of electric dipole, then it will be 2 kp cos theta divided by r square. This is the formula now. Kp cos theta y r square, sorry. Hamza, do you remember the formula?
No, sir.
Okay. So at point P, the dipole is Kp cos theta by r square. Okay. So K is constant, dipole moment is constant, this distance remain constant, and we have to find the value of potential. At what point the potential will be maximum? Maximum means this cos theta should be maximum. Cos theta should be maximum. So you can write this simply. Cos theta is maximum. So what is the maximum value of cos theta? When theta is equal to 0 degree and theta is equal to 180 degree. Okay. So when theta is equal to 0 degree, then cos theta is 1, and when theta is equal to 180 degree, here theta is equal to 0 degree. Theta is equal to 180 degree, then cos theta is equal to -1. So theta is equal to -1, and we have to find the value of here theta is 0 and 180 degree. These are the cos theta is maximum when theta is 0 and 180 degree. So this theta will become 0, means this point will lie, means this point will come somewhere like here. Okay, here the value of potential will be maximum, and if you do this to this OP, then this point P will lie here. So there are two positions. There are two positions. When theta is equal to at theta is equal to 0 degree, the value of potential is 0, and theta is equal to 180 degree, the value of potential is 0. Well, value of potential is maximum. So you can write here, you have written in the answer that at theta is equal to 180 degree. That is half correct. Okay. So you can say at theta is equal to 0 degree and theta is equal to 180 degree, the value of potential due to dipole is 0. Why this is 0? Because cos theta will equal to become 1, then we will have the value kp by r square. That is the maximum value. Okay, this is maximum. If suppose if theta is anything else, like theta is 90 degree, so Vp will become 0 now. And suppose if theta is something 60 degree, then it will become half. So the value of potential will be maximum only at angle 0 or 180 degree. Okay. So this is the question. So you can simply write at theta is equal to 0 and theta is equal to 180 degree, the value of potential due to dipole is 0, not 0, maximum. Is maximum. So there are two positions like this. There is one this position and there is one this position. Have you understood? Hamza?
Yes, sir.
Okay, fine now. There is no doubt.
No, sir.
Okay. So we have done this question. We have done this question. So here the work done is 0, and here the potential. What are the points at which, at points at theta, you can say on the, and one thing more here, on the axial line, on the axial line of dipole, the potential is maximum. So there can be 2 points on axial line, like here you can say. On the axial line, there can be only 2 points. Suppose this is charge minus q and this is charge q. There can be only 2 points. Here is another 1 point. Here is another point. Here is theta is equal to 1. Theta is equal to 0 degree. Here theta is equal to 180 degree. This is the answer of this question. And now this is the question. How much work is done in moving a 500 microcoulomb charge between 2 points on equipotential surfaces? So let's see this question. Work done is equal to charge into change in potential. Work done is equal to charge is given 500 microcoulomb and change in potential on the equipotential surface. What is the change in potential, Hamza, on equipotential surface? Suppose this is the equipotential surface A and B. What is V minus A? Suppose I am taking charge from A to B. So what is the value of VB minus VA? This is equipotential surface. Equipotential. Hamza?
Yes, sir.
What is the change in potential? What is the change in potential on equipotential surface? On equipotential surface, the potential of every point is 0, same na?
Yes, sir. It's the same.
So means the potential is not changing. Means delta V is 0.
Oh, you're saying the change in potential. Okay, yes. It will be.
Yeah. I am saying change in potential. Change in potential. Sorry.
Yeah, it will be 0.
These value have same value now. VB minus VA equal to 0
Yes. They'll be.
because they are equal.
Yes.
So we can say work done is, the answer is work done equal to 0 degree. So see, these are very easy questions, except the question number 1. So another question is, what is the geometrical shape of surfaces due to isolated charge? I think you have done this correctly, but you should make the surfaces also. Like, what is the meaning of isolated charge? Is there is no other charge, like isolated charge, like I am considering a positive isolated charge, and due to this charge the equipotential surfaces are spheres, concentric spheres like this. Okay, please imagine these as spheres, as these are not looking like spheres. Okay, so we can say concentric sphere, and we should also draw the diagram in the examination. Concentric spheres. This is the answer of this question. This is answer number 1. So now should I move? We have completed this, and after that, Hamza, we have completed this now.
Yes, sir. We complete.
Actually, we have started in the chapter capacitor. Firstly, I have discussed what is capacitor, and we will study three types of capacitors. Okay, and symbol of capacitor we have done. After that we have done a numerical, and battery and capacitor both devices store charge. What is the difference between two? And after that I have told you about the parallel plate capacitor. Parallel plate capacitor when air is in between the plates. So we got the result like here. This result. The value of capacitance due to parallel plate capacitor is epsilon naught A by D. Okay, epsilon naught A by D. And now, if in between the plates, if I introduce a dielectric of some constant K, then the value of capacitance will become K times of capacitance in air. Okay, so I have told you to remember this formula and this formula only. But here the dielectric is fully filled. Like these are my hand, these two hands are the parallel plates of the capacitor, and if in between these plates there is fully filled dielectric. Okay, so the value of capacitance will be K times of capacitance when placed in air. And there is another case we have, case number third, parallel plate capacitor when dielectric is partially filled, not fully filled, means here dielectric is filled in a thickness T. Okay, and the distance between two plates of the capacitor is D, and I have derived the formula and we got this result. What is this? This is capacitance due to when dielectric is partially filled. Actually, this is not very, this thing is looking complicated, but this is not complicated. Okay, this is not complicated, believe me. Then we will solve the question, then you will get to know. So Hamza, till here everything is clear na in this chapter?
Yes, sir.
Actually, I want that you should revise your notes because actually it is very beneficial for you. Okay,
Yes,
for the
sir. I
exam.
will take my notes.
Yeah, for the examination point of view,
Yeah.
and try revise the notes is one thing, and there are some doubts also you may face some doubts. Then in the class, in the last 5 minutes or 10 minutes of the class, you should ask me the doubts. Okay, if you face any kind of doubt, like if you I'm giving an example, like if you want very small kind of doubt, very low level of doubt to very high level of doubt, you can ask me anytime. Okay, so this is the thing we have studied. We have actually studying the parallel plate capacitor, and what we are doing in that parallel plate capacitor, we are introducing air. Okay, sometimes we are filling air in between the plates of capacitor. Sometimes, suppose this is a capacitor. Okay, suppose this is a capacitor. Capacitor is what? Two parallel plates separated by some distance, two oppositely charged parallel plates separated by some distance. And firstly, what we have done, we have filled the air in between the parallel plates capacitor. Then we have calculated the value of capacitance then capacitance is come out to be epsilon naught A by D. And after that, I have filled a dielectric between the two plates, and that dielectric is fully filled. Okay, and we have got the formula of capacitance as when dielectric is fully filled is K times of C naught, and C naught is epsilon naught A by D. So what is K? K is the dielectric constant, means in the in the in between the parallel plates, uh, there is dielectric, and that dielectric has a constant. We have studied in electrostatic also dielectric constant, and dielectric is non-conducting. Dielectric is not conducting means, okay. So and after that, what I have done, I have filled a dielectric again, but not fully, but partially, and we got this lengthy formula. And here A is the area of plate, epsilon naught is absolute permittivity of free space, or you can say air or vacuum. D is the distance between two plates. T is the thickness in which the dielectric is placed, and K is the dielectric constant. So now should I move?
Yes, sir.
Okay, let's see. Now what I am going to do this time, I am having these parallel plates, and I am filling these plates partially with a conducting medium, like parallel plate capacitor with conducting slab partially filled. Conducting slab is nothing, is a conducting, it is a slab which conducts electricity. Okay, and this is a slab also. Fourth case is parallel plate this fourth case is of parallel plate capacitor. Okay, parallel plate capacitor with conducting slab. Earlier we have introduced the dielectric slab. And what is the difference between the conducting and dielectric slab? A conducting slab conducts the electricity, a dielectric slab don't conduct the electricity. This is the difference. With conducting slab, you know what is slab? Slab is like, you can say this is a phone. Phone is a slab. Means a cube of small, a cuboid of small thickness. Conducting slab partially filled between plates. So this time what is happening? This time what is happening? These are two plates of capacitor. Here is one plate. Here is another plate. And these plates are parallel plates. Actually, Amjad, these are our previous plates. but this is a like this is these are the plates now. So what I have done this time, I have done this. You are seeing on this part of my hand. Sorry, this part of my hand. Okay. So there will be two parallel lines. So these two parallel lines are the parallel two line. This is one plate and this is another plate. And this is positive charge and this is negative charge, as we have discussed. Positively charged plate. Actually, this is a way of representing the uh, parallel plate capacitor. So no need to draw the diagrams again and again in the form of like cubes and like this. No, so it is easy to, and it also saves our time. So we represent the front view. This is negative charge, and now I am introducing a conducting slab. Now I am introducing a conducting slab. This is a conducting slab. This is a slab, but this is a conducting slab. And again, we have studied that I am taking the distance between two plates as d. Okay. And the conducting slab is filled in a thickness T only. Okay. In a thickness T only. So Hamza, as this is a conducting slab, conducting slab means conductor. And if I want to calculate the electric field at this point P, what will be the value of electric field, Hamza?
Sir, can you say again?
What?
Sir, can you repeat?
Actually, is my voice is not clear?
Sir, it's clear.
During the whole class, it was not clear.
No, sir, it's clear.
Okay, okay. Now please listen. I am saying that this is a conducting slab, and I want to calculate the electric field at this point. What will be the value of electric field here? As we have already discussed, the electric field inside the conductor is zero. Okay,
Yeah.
so this is a conductor. So means electric field inside this
Zero.
zero. And Hamza, here is air. This is a part in which the air is placed, and here what is the value of electric field? We have a formula, E is equal to sigma by
Epsilon.
epsilon naught. Okay, yes, due to both the plates. So I am writing it. EC is electric field inside conducting slab. You can say conductor also. We have discussed this many times. In case of conductor, the electric field is zero inside the conductor. And E naught, I am representing this E naught. E naught is represented by electric field in air between plates. Okay. between plates. And this E naught is equal to, due to both the plates, not 2 epsilon naught, sigma y epsilon naught, you can say here, due to both the plates. And what is the value for the single plate, Hamza? Due to the single plate, it is sigma by 2 epsilon naught. Okay. Okay, that's fine. So now we have calculated the electric field. We have calculated the electric field. So what will be the total electric field? Total electric field will be electric field in air plus electric field in conducting slab. Electric field in air is sigma by epsilon naught, and this will be 0 in conducting slab. So total electric field will be sigma by epsilon naught. I am representing total electric field with E suffix T. That is sigma by epsilon. And now I want to calculate the potential difference between the two plates. Now I want to calculate the potential difference between two plates. So potential difference between two plates is, we have a formula E equal to V by D. P is potential difference. This is D. So I can write potential difference is E into D, and E is E total. So we have potential. What is the value of E, Hamza? Sigma by epsilon naught.
Yes, sir.
But Hamza, there is one thing more. One thing more. Please tell me. Please tell me here. This, what is the value of this D? What is the value of this D?
D.
Actually, this not. This is not D. This is D minus T. Why?
D is small, right?
D minus T. Now you can see here. You can see here. This distance, whole distance is D, and the distance, now this is the distance of air. So it means that the electric field is in air is in the distance of D minus T. So we will take this distance, electric field is equal to potential upon D minus T. Okay. So E is sigma by epsilon naught, and this is D minus T. And what is sigma, Hamza?
Sigma is E epsilon 0 by.
Sigma is Q by A, charge per unit area. Sigma is surface charge density. Okay. Sigma is surface charge density. So here is sigma, and sigma is surface charge density. And surface charge density sigma is given by charge upon area. So I will put this QYA in this equation. I will put this sigma here. So we have potential is equal to, what is the value of sigma? QYA and epsilon naught, and this is D minus T. This is D minus T. So now we have the potential difference between two plates. Now can I calculate the capacitance? Capacitance is equal to Q by V, and Q is Q because I have given plus Q charge here and plus Q charge here, okay, minus Q charge here. So I am taking the magnitude of charge. And what is potential? Q divided by A epsilon naught D minus T. Okay, Hamza? And this Q and Q will cancel out and we will get epsilon naught A upon T minus T. This is the formula of capacitance. Epsilon naught A divided by T minus T. Hamza, is this class is boring?
Sir, what?
I am saying that is this class boring?
No, sir.
Okay, that's fine. So this is the capacitance. So what I am doing actually, firstly we have to calculate if we want to calculate the capacitance. So what I am doing, if you are observing things, what I am doing, firstly I am calculating the electric field, and from that electric field I am calculating the potential, and from that potential I am calculating the capacitance. Okay. I am doing nothing special. So this C is also greater than C naught. C naught means the capacitance of plate when air is in between them. Do you want to note it down, Hamza?
No, sir, I took screenshot.
What? Actually, your voice is not clear.
Sir, I took screenshot.
You have taken the screenshots?
Yes.
Okay. From here also?
Yes, sir, that was okay.
Okay. Completed. So there is one question. A parallel plate capacitor with air. Now you will see. Now you will understand the things more clearly. A parallel plate capacitor with air between plates has a capacitance of 8 picofarad, and 1 picofarad is equal to 10 to the power minus 12 farad. Okay, what will be the capacitance? What will be the capacitance if distance between the plates if distance between the plates is reduced to half, and the space between them, the space between them is fully filled with dielectric of constant six. This is the question. So now let's see the question very carefully. We have one parallel plate capacitor, no problem. Like I can make like this and this. I have one parallel plate capacitor like this. Okay. And this parallel plate capacitor is placed in air. Now this is in air initially. Air, and capacitance in air is represented by C naught. So capacitance is given by 8 picofarad. So I am converting this 8 picofarad into farad. So this will be 8 into 10 to the power minus 12. Okay. Now they are saying that, and distance is D. Finally, what someone has done, the distance between the two plates is reduced to half. Okay, and these whole plates are filled with dielectric of constant K is equal to 6. And now we have to find the capacitance of this when dielectric is placed. I am representing this by Cm. This is the question. And Hamza, we have one formula. Look here. But you should relate that formula. Cm is equal to K times of C naught. We know Cm is equal to K times of C naught. And we know the value of C naught also, epsilon naught A by D. C naught is epsilon naught A by D.
Yes.
Okay. C naught is Cm is equal to this. This is our relation. So the value of C naught is this. And I can write Cm as K. The value of C naught is epsilon naught A by D, means now you have to take this D na, because you are talking about the dielectric. D by 2. So this 2 will go in the numerator. So this will become 2K epsilon naught A by D. And we have the value of K. What is the value of K, Hamza?
Value of what?
That what is the value of K? Value of K. 6 na? K is 6.
Oh, yeah.
Epsilon naught A by D. And this is 6 to the 12. And what is this? This is C naught, and C naught is given by this 8 picofarad, means 8 into 10 to the power minus 12 farad. So this will become 96 into 10 to the power minus 12 farad. This is our required answer. Cm will be 96 into 10 to the power minus 12 farad. This is the final answer. Have you understood the question?
Yes, sir.
Firstly, the air is filled in between the plates. So we have C naught for air. We have already discussed C naught here. Like this, Cm is equal to C, or value of C naught is epsilon naught A by D. C naught is epsilon naught A by D. In the next class, I will write all the formulas for you, which will be used in the numericals. So this is initial condition, and finally our dielectric is filled fully, and we have this formula. We have used Cm. Cm is equal to K epsilon naught A divided by D by 2. Hamza, is there a class today? Today is also the class of us.
What?
There will be class today. There will be the class today of yours. Sorry, what I am saying here. Tomorrow there will be a class or not with me.
Sir, I don't know.
You don't know. Okay. So Hamza, this is the thing. Please revise the notes, and after that you will get to know what is happening here. Okay. Have you noted? Hamza, noted till here?
Yes, sir.
Okay. So Hamza, please tell me what is charge? Charge.
Sir, something.
Hmm? Bolo, what is charge? Don't know.
Sir, it's property of matter.
हाँ सही बात है. You are right. Very good.
It is positive or negative.
Okay, fine. And what is the formula of potential due to means you are like here is a charge Q, and I want to calculate the potential at this point P, and distance is R. Potential at point P will be, what is the formula? This is a charge, and this charge is at a this point P is at a distance R from this charge, and I want to calculate the potential at point P. What is the formula? Do you know? This is given by KQ by R. Okay, that's fine. And we have one or more formula. The work done is equal to charge into change in potential. V final minus V initial. Okay, Hamza?
Yes, sir.
Okay. So actually there are few more topics in this chapter, and after that there is one very easy chapter known as current electricity. Actually, electrostatics, I think, is the toughest part of the syllabus of 12th. In electrostatics, basically electric field and charges and potential and capacitance. These units are, I think, little bit typical for the students. And after that, there is current electricity. That chapter is very easy chapter. Okay. And Hamza, what is Coulomb's law? What is Coulomb's law?
Um, Coulomb's law.
Please,
Law
increase
states
increase your voice. Increase your volume.
yes, sir.
Actually, your
Coulomb's,
voice is not clear.
sir, Coulomb's law uh, states that the force of attraction or repulsion
Yeah, yeah.
between two charged bodies is directly
Very good, very good.
yeah, it's
Means
directly proportional
you know the
to the
things.
force
Yeah,
of
you know the
attraction.
things.
Yeah, and then inversely proportional to the square of
Okay, okay. Good. That's fine. That's fine. This is the Coulomb's law. And who is Coulomb? Coulomb is a human, and he's a
yes, sir,
scientist.
he's a
He's a
scientist.
scientist also.
Charles
So, uh, do you know about this person? Newton,
Sir Isaac Newton.
Sir Isaac Newton. Actually, he was very brilliant person. And there is one more Albert Einstein. There is one more Nikola Tesla. Okay, so these are very genius persons. And you have told me that at that time you like to play table tennis or football.
Um, I like to play
Ta-
tennis and badminton.
You like to play,
Badminton.
okay, badminton. Okay. So who is the top player of badminton these days?
Sir, I don't know this play.
Hmm?
Sir, I don't really see sports news. I just like to play.
Okay, that's fine. Okay. And Hamza, uh, what is electric field? How will you define the electric field? Electric field.
Sir, what?
Uh, my voice is not clear. What is happening? What is electric field?
Electric field. It is it is a space around the charged
Very good, very good, very good.
where you can
Fine, fine,
see the force.
fine. Okay. And what is capacitance? What is capacitance? I have given a very beautiful example here.
Sir, I don't remember.
You don't remember?
Yes.
Okay, no problem. Like what? Where we have
Sir, I
done the
remember, it is the ability to store, I guess, store the charge, no?
huh?
Yes.
Capacitance is the ability to store the charge. Simple. This is capacitance, charge holding capacity of conductor. Okay, Hamza, that is fine, but please, these things are looking complicated, but not that complicated because you can think of that. This whole world is made by Allah. Okay, so actually we are studying those things now which are made by Allah. So so these things are not that complicated, but you should give some efforts. You should give some efforts. After that, you will get to know whether these things are complicated or not. Okay. Give at least 1 hour or 2 hours for revision. At least 1 hour or 2 hours. In a day, there are 24 hours, and I believe 8 hours a person can work. And from that 8 hours, uh, you should give 2 hours. These days are your vacations. These are your vacation days.
Yes, sir.
So you can give at least 1 hour or 2 hours. Like I just today I have done this now. Today I have done this thing. So please try to understand what I have told you. If you are not comfortable, you can take the help of book also, any book also. You can take the help of me also. Okay. But at least try. Okay, that is fine. That is fine, Hamza. Sorry. Okay, now Hamza, you can leave the meeting and